In this video, we're going to talk about the inverse of a matrix. And what you see here in front of you is two equations, and the first one basically would be one way to define the inverse of a matrix, and that is some kind of matrix that when multiplied by the original matrix gives us an identity matrix, which is denoted as I. And an identity matrix is essentially a matrix consisting of zeros, except for the main diagonal going from the top left to the bottom right, which consists of ones. So that's your identity matrix. And another way to define it is it's the inverse of the determinant of the original matrix A multiplied by the transpose of its coefficient matrix. We will take a look at what coefficient matrices are in just a second. But for now, just bear in mind this definition, and the necessary requirement for the existence of an inverse to a matrix is that the original matrix has to be square and the determinant of the original matrix should not be equal to 0. So in case of the determinant being 0, the matrix is called singular and it has no inverse, so it doesn't even make sense to try to find the coefficient matrix, etc., etc. So the determinant is really a handy tool to see if it even makes sense to continue with finding the inverse of a matrix, and we will later see the same pattern applies to the Cramer method, which is a method of solving systems of linear equations. That's going to be another video. But for now, let's try to find the inverse of a 2 by 2 matrix. And we have this little matrix M, 2, 3 in the first row and 5, 4 in the second row. So right off the bat, let's find the determinant and see if we should even pursue finding the inverse of this matrix. And the determinant of M is going to be equal to 8 minus 15 or negative 7. So it's not 0, makes sense to continue, and then the next step is going to be finding the coefficient matrix to matrix M. And the coefficient matrix is essentially, in this case, it's going to be just like we did with the minors in the determinant. We cross out the row and the column of each element, so starting with 2, and we find the coefficient of this element. So the coefficient matrix is going to be equal to the original matrix. It's the same size, and in this case, our coefficient matrix, we'll call it C, equals to 4. So we cross out the first row and the first column, and we get 4. Then we do the same for 3, and we get 5. So it's 4, 5, and then for the second row, it's 3 and 2. But we are not done just yet. An important thing to do is remember the chessboard of pluses and minuses that we used before. So the so-called symbol matrix. And we need to multiply the second term of the first row and the first term of the second row by -1 in order to fulfill this requirement of the equation matrix. So now what we get is 4, -5, -3, and 2. We can now find the transpose of this coefficient matrix C, and this is also something that's sometimes called an adjugate matrix. So we transpose it and we get 4, -3, -5, and 2. The last step is multiplying the inverse of the determinant. So in this case, it's going to be 1 over -7 by the adjugate matrix that we just found. And this essentially gives us our inverse of matrix M. And I say it's a good idea to leave this 1 over -7 out, just so that we avoid those nasty fractions if we try to multiply every term by 1 over -7. And there you go. So that's that for a 2x2 matrix. And for your homework, I want you to try and figure out the inverse of this 3x3 matrix, which we will cover in a separate video. So we will provide a solution for that. Just remember to keep in mind the chessboard symbol matrix when you're finding the coefficient matrix. And I say everything else should be quite straightforward. Just follow this example, and good luck. Don't forget to check out our other math videos and subscribe for more.